Here we go. We've got two more rules to learn in this video. And the first one is going to be about the natural exponent. We'll start with that one. The second one is going to be taking the derivative of any exponent. So here we have natural exponent. This might be a time function. So the derivative of the natural exponent is itself. And that means if I want to take the derivative of this thing, I'm just going to end up with e to the t. And notice that the relative change that's my derivative over the function itself is just equal to 1. And so this is like saying the relative change is always 1. And that's actually what the natural exponent is supposed to do. Now let's look at the natural exponent with the chain rule. So more often than not, there's going to be something inside the exponent that we're going to have to consider when we're taking the derivative. So here we've got a new function, and we're being asked to take the first derivative and the second derivative. So df over dt is going to be equal to the function itself. But notice that I could write this as 2f of g of x, where f is equal to the e function, and g is going to be equal to 2t. And maybe I should have a 2 on the outside there. And maybe put a t up there. So now when you're looking at this thing right here, you can see that it's actually a composite function. That there's the natural exponent, which represents one function, and then in the exponent is a second function. So we're going to want to use the chain rule here. So the first we take in the derivative of essentially the outside function. Now I want to take the derivative of the interior function, or the kernel, and it's 2 times t, so it's just going to be 2t to the 1 minus 1, like so. And the first derivative is going to be equal to 4e to t. Now, what is the second derivative going to look like? Well, I'm going to take the derivative of this thing here, the first derivative, take the derivative of the first derivative, and we're going to get 4e to t multiplied by the derivative of the kernel, the interior function, and we get 8 times e to the power of 2t. Why don't you try this next problem? Take the first derivative and the second derivative of this natural exponent function. If you'd like to keep working on your own, I encourage you to press pause. Otherwise, let's walk through it together. And so if we start with the first derivative, we get the derivative of the exterior function, that natural exponent, is just itself. And then what have we got up here? We've got a t squared. What's the derivative of t squared? Well, it's 2t. And there's our first derivative. Now, what about the second derivative? I want to take the derivative of the first. Take the derivative of the first derivative, I should say. And again, I've got, what have I got here? I've got a product. So I'm going to have to use the product rule. And I'm going to have to use the chain rule again. So let's, let me remind you what the product, well, no, let's just keep going. So I'll take the, apply the chain rule to find the derivative of the first product. And we get 4et squared times 2t multiplied by this thing, right? The second product, plus 2, the derivative of this thing here, multiplied by 4et squared. And I can do a little bit of simplifying here. I can write 4et squared, and now I've got 4t plus 2 inside there, and then I could factor out a 2. So I've got 2t plus 1. And there is our second derivative. And did you see my mistake? So I made a small mistake here. I forgot my t squared. I forgot my square on the t there. What about exponential functions that are not the natural exponent? So we have a base that's not equal to the natural exponent. So in this example here, we've got a to the power of x. So a is some other base. How are we going to differentiate this? Well, I haven't been showing you proofs, but this one is pretty easy and straightforward, so I'll show it to you. I can rewrite this as f of x is equal to, well, I know that a is equal by definition to e log a. Right? That's just equal to a. The natural exponential and the log are going to cancel each other out. And so f of x is going to be equal to, in this case, e log a, and that whole thing to the power of x. And when we've got this whole thing, including the base, to the power of x, we can rewrite it as e log a times x. Make sure that we separate the log a from the x. It's not log a of x, or it's not the log of ax, it's the log of a, that whole log multiplied by x. That makes sense. And if I take the derivative of this thing, right, what do we get? Well, we apply that natural exponent derivative rule that we already learned, and we get that. Multiplied by what's in the exponent, that's the chain rule, right? We got to use the chain rule. And if we take the derivative of the exponent with respect to x, we just get log a. This exponent, that log, they are going to cancel each other out. And, well, specifically, let me put the x back into its original position. And now we've got ax log a. And that, my friends, is the exponent rule with exponents other than the natural exponent. And that's rule 7. Kind of fun. I can tell you that this is the least commonly used function in economics. Or, well, let me be careful with that. It's not the least used function. It's the function that we take the derivative of least often, I would say, in my experience. We don't have to apply this rule too often. Occasionally it comes up. We still want to know it, but it's kind of a little bit cumbersome, and we tend to try and avoid it if we can. Let's do some examples together. So we'll start with f of x. So we have an exponent function, but it's not the natural exponent. And so if I apply the rule, I'm going to get the function itself. Now notice we've got a negative x in the exponent, so I have to use the chain rule, and the derivative of that exponent with respect to x is just -1, and log times the base, log 10. So we end up with f prime of x is equal to -10 negative x log 10. Now, I could do it the long way, right, like we did before. I replace 10 with e log 10. Right, the negative x is multiplied by the exponent according to the exponent rules. We saw that way back chapter 2 in an ALEX. The derivative of this thing is itself. Multiplied by -1 multiplied by log 10. And then returning just do a little cleaning up here. Times log 10. And we can see that we've got -10 negative x log 10. Which is the same thing we got by applying the rule and not forgetting the chain rule. We had to apply the chain rule. Now let's take a look at the next one that we have. No natural exponent here, and it looks like we've got to apply the product rule. So there's one product, and there's the other product. So I'm going to take the derivative of the first one. That's easy, it's just 1. Times 2 to the 3x plus, so there's the first product. Then straight away I just rewrite the exponential function itself. I can write the log of its base right away too, so log 2. Now I need to take the derivative of the exponent itself. So there's a 3x up there, the derivative of 3x with respect to x. That just gives us 3. And now all I'm left with is to simplify this a little bit. So we've got 2, 3x plus x, 2, 3x, log 2, well, let me be careful, log 2 times 3. And I can make it just a little bit easier by factoring out the 2, 3x. We're left with 1 plus 3 log 2. Here's a problem for you. It's a tricky one. You're going to have to use the chain rule. And you can see there's a whole bunch of smaller functions floating around in this function. So give it a try. Press pause in the video. Give it a try yourself, and then we can go through the solution together. All right, so I want to find f prime t, the first derivative. I'm going to start by taking the derivative of the outside. Oops. Try rewriting that t. Minus 2t. And then we're just left with a 2 minus 1 out there, so there's going to be a 1. Now I want to multiply it by the entirety of the inside. So I'll start with this thing. And I've got e2t times 2, right, when I use the chain rule, minus 2. And I'll close the bracket, and I guess that's it. As long as we know what we're doing, it doesn't take too long. Now all we have to do is some simplifying. It's not super obvious to me how to make this easier to look at, but one thing we could do is we've got 2t minus t in that bracket there. I can factor out a 2 here. So we've got a 2 there. And then I can rewrite this as just 4 e2t minus 2t minus 1. And I'm not sure I can do anything better with this than what I've done.